Rajendra Bose is best known in statistics for his systematic development of the mathematical theories of experimental designs and information codes. Throughout his work on balanced incomplete block, partially balanced incomplete block, and orthogonal Latin square designs, and on error-correcting codes, there is an interplay of ideas based on the physical properties of designs and the abstract properties of finite mathematics. As these become more tightly bound, the various types of designs and codes become more clearly related, and the suggestion of relatively few underlying mathematical principles emerge. The first and most celebrated instance of this is the Bose and Srikhandi disproof of Euler's conjecture that the orthogonal Latin squares of order 4t plus 2 do not exist for any positive integer t. It is a result equally important and interesting to statisticians and mathematicians. This program is devoted to the middle years of Professor Bose's career, when the majority of his important contributions to design and coding theory were discovered while he was professor of statistics at the University of North Carolina, Chapel Hill.
Now, another very dramatic thing occurred about that time. You know, the emigration of German talent during the Hitler years is one of the very important parts of the history of science. And about that time, as dramatic a piece of this history as any, I think, was the arrival of Friedrich Wilhelm Levy.
Yes.
As your head of the math department, right?
Right. The head of the math department suddenly died. He had a heart attack. And Professor Levy, Friedrich Wilhelm Levy, he became the head of the department in the University of Calcutta. I was already in the institute by that time, because Milanovic got 2 federal posts created, one for me and one for S.N. Roy, and we gave up the Asutosh College and moved 100% to the institute. He had done enough testing and he was satisfied with us that these are good people. But when Professor Levy came, I started going to the seminars he was giving. He wanted to change the syllabus because he found the syllabus of the Calcutta University very old-fashioned. And especially he wanted to introduce the modern algebra, which was called modern algebra at that time. It is no longer modern.
Yes.
The algebra of rings, fields, modules, ideals, things like that, and finite geometries. The professors at the university, they said, now this German has come and he wants to learn all these new things. It's terrible. So Levy told me that, look, I am writing a book on finite geometry and I am writing a book on algebra, and my English is not good. You correct the proofs, and if you don't understand it anywhere, you ask for my help. and I will give you a part-time job in the University of Calcutta to teach some of these subjects.
I see. And that's what you did.
That's what he exactly did.
And that was the beginning of you and the finite fields and the finite geometries.
Yes, the beginning of application to statistics came like this. The greatest statistician at that time was R.A. Fisher.
Sure.
And he was invited as a visiting professor to the institute by Professor Maloney. He came in 1938, 1939, and he had, at that time, he was interested in the construction of designs, which are certain patterns which are useful for finding differences between various kinds of treatments. And he was interested in orthogonal Latin squares.
Mm-hmm.
Now, he said that I conjecture that orthogonal Latin squares of every prime power order can be constructed, but I have only squares for 8 and 9 which I have constructed with great labor. Now, I realized that, well, the number of elements in any finite field is just a prime power, so the two things must have something to do. And I soon saw the connection. And I told him that, well, I can use my finite geometries to construct all squares like this. Of course, at that time, neither he nor I knew that McNish had already proved this back in 1922. By other methods,
Yes.
not using finite geometries.
Well, orthogonal Latin squares were just the beginning of your application of finite fields and finite geometries to the construction of experimental designs. Tell us some more about the fundamental work that began with Fisher's visit.
Well, one thing was that he was at this time very busy with the proof sheets of the second edition of Fisher and Yates tables for medicine, agriculturists, and engineers.
Yes.
Now, there was one table in it which dealt with balance in complete block designs. And there were certain gaps in that table. And he wanted to construct those designs. I told him that I think that maybe I can use my finite fields and finite geometries for the purpose of constructing designs.
Mm-hmm.
And one particular design I constructed from him right while he was there. The clue was suggested to me in this way. There was one design which he already had, namely the design in which there are 11 treatments and 11 blocks, and each pair is replicated twice, and the block size is 5, and there are 5 replications.
Mm-hmm.
I noticed that he had developed it cyclically from one given block. Now, I thought like this, what is in this one block which makes him come out with the correct solution? And I found that if we took all possible differences, mod 11, of these 5 things,
Yeah.
then every non-zero difference is replicated exactly twice.
I see.
I at once saw that if I use the powers of the primitive roots of a finite field together with their properties, then I would be able to produce such systems. Of course, then I told him that not every design will come by this way, then various modifications will be needed. And he said, all right, you do as much as possible and make up a paper and send it to me. I will publish it in the Annals of Eugenics. Thus came to be written that paper called the Construction of Balanced Incomplete Block Designs, which is now a classic.
Yeah.
In 1939, it is referred to in every textbook now.
Yes, yes.
Another thing that I realized was that in the case of factorial designs, if we represent, every treatment can be represented as a point in an affine space. And once after this representation is done, the degrees of freedom, etc., can be very nicely pinpointed in this picture. So we got, I took Kishan as my colleague at that time with me. I said, let us finish up this work.
Yeah.
And we wrote a small paper on that. Also, sometime later in 1947, I was able to answer a question which proved to be very important, which Fisher himself has raised. The question is this: suppose each factor is at S levels, S being a prime or a prime power, and we have blocks of size S to the power R. We want to make a factorial experiment so that no Tth order interactions or lower order interactions
Yes.
are confounded. What is the maximum number of factors that we can accommodate in this experiment? Fisher had answered this question for 2. That is, all the first order interactions or 2-factor interactions should be unconfounded. I answered it for the general question, for the general value of t.
I see. And you again using these methods of
these methods, representing the points in affine space, and extending it to projective space to interpret the degrees of freedom, etc.
Very good. Now the next visitor to Mahalanobis's Institute in 3940 was Harold Hotelling from the United States. And his interest in your multivariate work led to some very profound consequences. Would you give us that sequence of events?
Yes. What happened was he looked at the multivariate work which I and Roy had done, and as I had told you, Mahalanobis's D square is virtually identical to the non-central distribution of Hotelling's D square.
Yeah.
And he said, well, I will invite both of you as visiting professors in successive years to Columbia University once the war is over. The war had already started in Europe in 1940 when he came to us, but America was not in the war at that time. And he kept to his promise. He invited me in 1947 as a visiting professor. By that time, he had moved to the University of Chapel Hill to set up this new department of statistics, mathematical statistics there. And so Wald had become the head of the department at Columbia University. So I got an invitation to teach the winter semester at the Columbia University, and the next semester at the University of Chapel Hill.
Yeah.
After a short time, I also got an invitation to teach during summer
I see. Yeah.
at the Virginia Polytechnic Institute.
Yeah. That was
And then while I was teaching, finished at Columbia, and while I was teaching at Chapel Hill, I got an invitation to teach the first summer session at the University of Berkeley, California.
Mm-hmm.
So I had 4 invitations and spent 1 complete year in the United States. By the time I had gone back, I had an offer from the University of Urbana, Illinois, and an offer from the University of North Carolina at Chapel Hill to come to the United States if I wished as a full professor with tenure.
Uh-huh.
And thus I happen to be here now.
And that you did a year later,
Yeah.
right?
I went back to India, was there for about 7.5 months,
Yes.
and joined the University of Chapel Hill
Mm-hmm.
in March 1949.
I see.
My wife came 2 months later in June.
You were at the University of North Carolina, Chapel Hill from 49 to 71.
49 to 70.
And at the beginning, what you did was finish sorting out all the ramifications on classical experimental design. Balanced incomplete block designs, partially balanced incomplete blocks, factorial designs, and a lot of newer ones related to them. How did you have a plan for this? Did one thing just lead to another, or did you have a kind of a schedule?
I didn't have a kind of a schedule at first, but I found that my partially balanced designs, the definition we had given was really too difficult, and bits and pieces of them were being discovered here by other statisticians. I'll give you a true story. At the Oak Ridge meeting, about 1950 or 51, I do not remember, Professor Yoden described what he called linked block designs.
Yes.
He looked at me and said, well, I do not know whether these Indian statisticians have it tucked away somewhere in one of their papers.
Yes.
And
you had.
at the end, in the discussion, I said, yes, Professor Yoden, I plead guilty to your charge. It is given in the Bose-Nair paper of 1939, but it's given in an abstract form in a few lines from which it can be worked out.
Mm-hmm.
Miss Cox, the director of our institute of Statistics, because there were 3 departments in Chapel Hill, you know.
Yes.
The Department of Mathematical Statistics, in which I was employed,
Yeah.
and the Department of Biostatistics,
Yeah.
and both of these were at Chapel Hill,
Yeah.
and the Department of Applied Statistics at Raleigh.
Yes.
And all the 3 constituted the Institute of Statistics at North Carolina.
Mm-hmm.
And Miss Gertrude Cox was the director of the institute, and there were 3 separate heads
Yeah.
for each department. Miss Cox told me, boss, this would never do. You must write your partially balanced designs in such a form that everybody can understand them. And the first thing was to simplify the definition.
Yes.
And I came to the concept of the association scheme. The proper association scheme for the linked block designs of Yoden struck me right then and there at that meeting.
Uh-huh.
I went up to the board and drew up a square and showed that if we make this association scheme, and then base the design upon this in following manner,
Yeah.
then your link block designs would come. And this is implicit in what we have done in our 1939 paper, but not shown explicitly. So there was a student named Shimamoto who was working under me at that time for his master's thesis. And I asked him to work out the various association schemes and to show which design belonged to which association scheme. Next, then we wanted to introduce, to study deeply the properties of designs coming from each association scheme. For example, the group divisible association scheme was studied by Conner in his paper, though he had some other things also in his thesis. The construction of the designs belonging to the group divisible association scheme were done by me and Srikande and another Indian student by correspondence. And then we went on to other things. I cannot relate the whole story.
Yeah, but there was a kind of plan.
Ultimately it ended up with a very nice linear associative algebra, which is now called the Bose-Messner algebra, and which has been used also in group theory and in coding theory, which I did not know at the time that it could be so used.
The same power of yours of constructive proof was used the same year to demolish a long-held conjecture made in 1782 by the great Swiss mathematician Leonhard Euler. Check me on this to be right. He had failed to find a way to arrange 36 military officers, one of each of 6 ranks from each of 6 designated regiments, into an honor guard array of 6 rows of 6 officers each, so that each rank would be once and only once in each row and in each column, and each regiment would be once and only once in each row and each column. This was the famous problem of a 6x6 Greco-Latin square. Latin letters, say, for rank and Greek letters for regiment, or of 2 orthogonal Latin squares of order 6. Now, and Euler had proved that such pairs exist for all edge sizes bigger than 2, other than even numbers that you can't divide by 4 evenly. And having failed for 6, and I think we could suppose for a few others he tried out of 10, 14, 18, 22, and so on, he conjectured the non-existence of such pairs whenever the edge size was of the form 4t plus 2. Now, how did you and your student Shrikanda and E.T. Parker of Remington Rand Univac become known as Euler's spoilers?
Yeah, I must first explain to you what is a prime power decomposition of a number is. Say 12 equal to 2 square times 3.
Yes.
So the prime power decomposition is 2 square, comma, 3. The prime power decomposition of 21 is 3 times 7. In general, every number can be written in the form p1 to the power alpha 1, p2 to the power alpha 2, p3 to the power alpha 3, pn to the power alpha n, where p1, p2, p3, pn, they are different numbers.
Yes.
Now you take the prime power decomposition and take the least of these. This is a very important function. For example, for 12, it will be 3, not not 2 square, because 2 square is 4.
Yes.
Now Macnish in 1922 purported to prove that the exact number of orthogonal Latin squares
Yes.
of any given order is equal to, you take the minimum value of the prime power decomposition
Yeah.
and 1 less than that.
I see.
For example, if there is a single number, p1 to the power n, power of a prime, then we can make p1 to the power n minus 1, so many orthogonal Latin squares.
Mm-hmm.
He was, of course, right in that.
Mm-hmm.
Also, he was right in saying that we can make at least so many.
Aha.
For example, if you take the prime power decomposition, take the least factor and reduce it by 1, then Macnish was right in saying that we can make at least as many Latin squares.
I see.
But unfortunately, his proof was wrong for the other case.
Ah.
That is, perhaps we could make more.
Mm-hmm.
At least his proof was not correct. Levy showed to me in 1936.
No, that far back.
Yes. His proof being not correct does not mean that his conjecture is not correct. Might be it could be proved in some other way.
Right.
Parker first showed that Macnish's conjecture was really wrong in the other direction. Take the number 21. It is equal to 3 times 7, so that the minimum value of the factors is 3.
Mm-hmm.
1 less than that is 2. But he actually made 3 orthogonal Latin squares.
Aha.
So Macnish's conjecture was proved wrong. If Macnish's conjecture were right, then Euler's conjecture would also be right.
Mm-hmm.
Because if you have a number of the form 40 plus 2, then its prime power decomposition would be 2 times an even number and an even number and 2 times an odd number.
Yes.
And an odd number decomposed, all its powers will be powers of odd numbers. So the least value will be 2, 1 less than that is 1. So we could never make a Greco-Latin orthogonal Latin squares of order 40 plus 2.
Of course.
Therefore, when Parker published this paper, I had just come back from attending the International Math Congress at Edinburgh and the International Statistics Congress at Belgium.
Mm-hmm.
And my chairman, Dr. Nicholson, showed it to me. Now, Parker's method was not powerful enough to disprove Euler's conjecture.
Mm-hmm.
But it threw a grave doubt on it.
Yes, sure you would.
And Srikhanda and I started work on it. Srikhanda was a visiting professor with us at that time. It was the end of 1958 when we started work on this problem. And Srikhanda and I succeeded in finding a counterexample. The first counterexample found was 22. We had a number of theorems, and the first counterexample was found to be of order 22. This was published in the Journal of the National Academy of Sciences.
I see. In other words, you did produce 2 Latin squares orthogonal of side 22.
Yes. We had got the method in the morning. At night we had a party at home, and I wanted actually to make these 2 squares to satisfy myself
Yes.
whether our method was correct. And I sat up till the end of the party. Then I told my wife to go to bed. I have to construct these squares. I did construct these squares, and satisfied myself that our method was correct.
Did you use Roman and Greek letters?
No, ordinary
No.
numerals, 1 through 22.
I see. That was somewhat easier.
Yes.
Yeah, very
And
good.
then sent off this paper. Then next is Srikhand and I refined our methods, and we were able to produce an infinity of cases
Aha.
in which Euler's conjectures were wrong. Now, Albert, to whom I had sent my paper, communicated my paper to Parker,
Yes.
and he also started on the problem.
Very
And
good.
he also produced an infinity of squares by other methods
Very
in
good.
which Euler's conjectures were wrong. And a correspondence ensued between us. And then between the stream of three, we ultimately showed that if t is greater than 1, that is if the number is greater than 6, then we can always produce a Greco-Latin square.
I see.
So Euler was completely demolished.
I see.
And I used to go to the National Bureau of Standards many times. So it's the National Bureau of Standards people who gave us the title of Euler spoiler.
Well, what a pleasant term. Well, this kind of mathematical puzzle resolution is widely newsworthy generally, and it was in this case, was it not, when you read your signal paper on this before a meeting of the American Mathematical Society in New York. Front page of the New York Times, wasn't it?
Yes, our picture came out on the first page of the science editor of the New York Times came to interview us.
Yeah.
He made us put the square on the board, and he took our picture, and this picture came out on the front page of the New York Times. I was staying at a small hotel. The next day, when I went to pay my bill, this man says to me, "It looks like your picture on the front page of the New York Times." I said, "Yes, I am one of the three people." So he says, "You must have done something. The front page of the New York Times can't be bought for $1 million.
Well, this is a good press victory, wasn't it? Well, on the business of finite mathematical structures, or so-called combinatorics, you have been using them like this more and more ingeniously in applications to statistics and coding theory. Then in 1955, you opened up a whole new line of investigation, working on problems of coding theory with the tools of finite fields, finite geometry, finite algebra. Now, the inspiration for such significant innovations is constantly the study of historians and philosophers of science. What can you tell us about how the ideas hit you to take this new path?
Well, firstly, I was at the end of my tether in the construction of various kinds of designs. We had explored all of them. And I was looking for a new subject. Right at that time it happened that Professor Schutzenberger of France
Oh, yes.
was a visiting professor at Chapel Hill. And he was, of course, attending my seminars. And he said, "Bose, why don't you look at Slepin's paper? It seems to me that maybe the methods you are using here would work for coding theory too."
Mm-hmm.
And I looked at Slepin's paper, and I remember you were my first student in this coding theory business. And we tried geometrical methods.
Yeah.
We got enough material to get you a PhD degree, but we couldn't go very far.
That's true.
The next student who came along was D.K. Ray Chaudhary. And when he came along, I realized that this extension of Fisher's theorem, the what's the maximum number of factors that we can accommodate,
Yes.
so that up to no t-factor interaction would be confounded. This might be useful in constructing codes, because in a way, in the code, what do? We send a message symbol, a number of symbols as the message sequence, and calculate some other redundant symbols from these, and try to have a method of calculating these redundant symbols in such a way that when the whole string is transmitted at the other side, it can either be used for detecting whether this message is wrong, and should we ask for retransmission, or we can correct up to a prescribed number of errors. That is what a code is. Now, each symbol can be regarded as a sort of factor. For example, if we have a binary code, 010111101, etc., like this, then we can think that there are two factors. In a block of n, we can think that there are n factors, and each factor is at either level 0 or is at level 1. If it is a ternary code, we can think that each factor is either at level 0 or level 1 or level 2. And I pointed out this theorem to Ray Chaudhuri and said, now look here, can you use this theorem to construct codes? And one error correcting codes had already been discovered by Hamming. But Ray Chaudhuri came out with a solution for a two-error correcting code using this theorem, or an analog of it. Then, after some time, he came out with another code, and he said that I can't prove it, sir, but this seems to be that this will correct T errors. And I was able to prove that his intuition was right. Now, this is in a way a reversal. In most cases, when PhD students work under me, the intuition is mine and the working out is theirs. But in this particular case, it happened that the intuition was his, and the work and the craftsmanship involved in writing that paper was mine. That paper was published in 1960. Peterson was present at that meeting, and it later on transpired that another French mathematician, Hockingham, had also obtained that same code by other methods.
And then these were the famous BCH codes.
Yes, B for Bose, C for Chaudhuri, H for Hockingham.
Well, fame came quickly to them at that time, I remember. One colorful forecast was expectation of one uncorrected error every 300 years of sending messages across a toll-grade telephone circuit. Was that estimate yours, or did it come from the press that covered the report you made to the American Institute of Electrical Engineers in a New York meeting in '61?
This was certainly published, but this is a journalistic simplification, because you must remember that the BCH codes are a class of codes, and they can be used either for two-way transmission or a one-way transmission, either with error detection or with error correction. So It's true that if you choose a proper code and a proper channel, then you can have a situation where there will be the expectation of error, just one expectation of error in 300 years.
I see.
Most probably, Dr. Peterson was at this meeting, and he writes in his paper in the Scientific American in 1962, he describes a channel where there will be exactly one error. Not exactly one error, where the expectation of error would be 1 in 300 years.
I see.
And those who are interested in this, there he describes what code we should use, what channel we should use in order to get this result. It's a popular paper in the Scientific American, February 1962.
Very good.
And those who are interested in it should read it.
Yeah.
Of course, this statement was published in the press earlier to that.
Yeah.
I think they must have asked Peterson,
Okay.
because Peterson himself was instrumental in discovering many new properties of the BCH codes. For example, he proved that they are cyclic codes. And once codes are cyclic, an instrumental gadget of transmission called the shift register can be very skillfully used
I see.
to actually make gadgets for transmitting this information.
Very good.
This work was being done at the Lincoln Lab of the MIT. All these details can be found in Peterson's paper.
Very good. All your work is distinguished by that wonderfully practical quality that existence proofs are constructive proofs. To prove the existence of something, you give a method for obtaining it. This was true of the Bose-Chowdhury codes, and there the practicality was made even more high because the procedure was readily attainable in engineering practice. How did the codes get into actual use, and are they still a major communications procedure?
I have already told you that the prototypes were built at the Lincoln Lab by various people, and there are two kinds of use that we can put those codes into. Either there is a one-way channel, or there is a two-way channel where we can detect errors and request retransmission.
Yes.
But the cyclic property of these codes was discovered by Professor Peterson.
Nice.
And that made it very easy to put them in practice. For about 10 years, these were the best practical codes that were known. Since 1970, Gopa has written about 5 papers, Chien and Choi 1973, one paper, which are generalizations of Bose-Chowdhury codes. You know, in research, every generation stands on the shoulders of the other.
True, true.
Delsart also has been worked on it for 5 years, from 1970 to 1975, wrote a number of papers. He uses the ideas of association schemes. It's very interesting. The association schemes were used by me, as you remember, to sort out partially balanced designs.
Yes.
But he found them useful in coding theory.
Now
I have no idea about how far the gadgetry of these things has been perfected.
Yes, I see. But the codes are going ahead, new developments almost all the time, I guess.
Yes, and some better codes than the Bose-Chowdhury codes are known now.
I see.